Welcome everybody, and we're going to go into chapter 5 today. So let's go ahead and head over to the PowerPoint for a little bit, and then we are going to do some work on the board as well. So, get down to here. So, we really have just talked about the gates. I know in some of my examples I have already started to combine some gates like this, like you see here. We talked about sum of products form, product of sums form, and so, you know, this is essentially a little bit of a refresh, at least for us, because I know, like in my last video, I did a combination, or where I showed that a NOR gate was the same as an OR gate and a NOT gate in series, or, you know, one feeding into the other. So I've kind of already gotten into the combinational logic, but all combinational logic means is using two or more logic gates to perform a more useful complex function. Okay? So you can see that both of these terms have D inherent to them. And so with this setup right here, how many gates would you need? Well, you would need one AND gate for this. You would need one AND gate for this. And then you'd need an OR gate for the whole thing, right? Both quantities. That's 3 gates. If you were to factor out that D and reduce it, now you've got a single OR, and then you take that quantity and AND it with a D. You've just reduced your gates from 3 to 2. That's good, especially if you're making something, you know, a million of something, and you want to use as little hardware as possible to make it as cheap as possible. You know, you can do something like this to reduce the number of gates that you're going to use. Okay, so this says write the Boolean equation for the circuit below. All right. Now I'm getting ready to take my microphone over to the board, and this week I've had an issue sometimes. If I'm not sitting right here in front of my computer, it starts clipping out if I turn my body. So I'm actually going to have this set over in my my marker well, I guess is if you want to call it that, and have it pointed at my receiver. So if you hear any clipping at all, let me know. All right. So I'm actually going to write this on the board. Keep that right there. Hopefully I've got that solved, but like I said, I'm watching the comments here, so if there is an issue with me doing this, just let me know. Okay, so let me write this down. There's 2 ANDs and an OR, right? So and that feeds into an OR. And we had, let's see, this is ABC. Okay? All right, and then we have output X out here. All right, so what I like to do when I go through this combinational logic is I like to give you the output at every single gate, okay? So the output of this gate up here is A and B. The output of this gate is B and C. Then I take this quantity and I OR it with this. So my final answer is X equals AB plus BC. Okay? So that's what it told us to do. It said to take that and write the Boolean equation for the combinational logic circuit. No problem. We did that. All right. And to reduce that down, we have a set of laws and rules, which some of them are going to be identical to what we use in just regular algebra. But remember, with regular algebra, you could have a variable that equals 5 million, right, or negative 600,000. With Boolean, the variable can only be 0 or 1, so we're restricted on what all we can do. But we are still going to use some of the same techniques, okay? So you need to know all 3 of these laws, and you need to know all 10 rules. All right? The first one that we're going to talk about here And I don't see any comments about the audio, so I'll just keep going here. So, commutative laws of addition and multiplication. This might seem super easy, right? The order of the variables does not matter. So, if I have a plus b, I can rearrange that to say b plus a, right? Remember, when you write these truth tables, you know, how you set up the columns is up to you. You could have it, the first column be b and the second column be a. It doesn't matter because they're just variables. And so the order of the variables does not matter in addition and multiplication, okay? So in the multiplication case, or the AND case, a times b is the same thing as b times a, right? Again, that might be self-evident, but we're going to point it out because we're going to use it. The next one is called the associative law. And this one's, and it's of addition and multiplication again, and you'll see both of these examples here. So the associative law for addition says that, okay, if we're ORing them all together, right, it doesn't matter which pair I do first, if I'm going to do them a pair at a time. So I could take B or C, get a result from that, and then take that as an OR with A, right? And so essentially you see you end up with the same equation on both sides. It's just the parentheses tells you that I'm going to do this first, and then I'm going to do this. Okay, same thing over here. This first, and then I'm going to do this. Okay, same thing with, you know, if you're going to do, if you're limiting yourself to 2 input gates, you can certainly do A and B first, get that result, and then take that AND with C, right? Or the other way around, do B and C first. I mean, for that matter, you could do A and C and then do B. Right? It doesn't matter which order you do them in, okay? And that's going to become important when we start to answer the question of, you know, how do you create a 3-input AND gate, which is what this would be if you said x equals ABC. How do you create a 3-input AND gate using only 2 input gates? And this is the answer right here. So if you're hearing that now, eventually you're going to be asked that question again. And so you're going to want to come back to, you know, or write it down right now that's how you do it, okay? All right, and then finally we have the distributive law, all right? Does anybody, can anybody, let's put this in the comments here. Anybody know what this is also called? Instead of the distributive law, what acronym do we use to remember how this works? So instead of the distributive law, what acronym do we use to remember how this works? And I'm talking specifically just in algebra. What method? There it is right there. Okay, so Steve got it. So FOIL. First, outer, inner, last. Okay? Yep, David got it too. FOIL, that's correct. So, this is essentially just FOIL. Now, if you just have something like this, okay, if you this is more of what I think of when I think of distributive law. This, you know, my algebra teachers have burned this into my memory as a FOIL condition here, right? So, we have, you know, the way this gets distributed out, if you have A times some quantities that are added together, it's always this times this plus this times this. You distribute this to each term in the parentheses, okay? Same thing down here. If now you have 2 of these quantities added together, multiplied together, you distribute the A over here, and you distribute the B over here. And so you've got A times C, that's the first, because it's the first term in each group of parentheses. Then you do A times D, the first, or I'm sorry, the outer ones. So those are like the outer ones, right, of each one, if you look at this as a whole. And then the next one is B times C. That's the inner. That's the I part of FOIL, right? This is the inside and this is the inside. If these are the outer, if A and D are the outer, then B and C are the inner. And then finally, we have B times D, which is last. So first, outer, inner, last, FOIL. Okay, and then you just add all those together. So these two equations are identical to each other in how they perform. Like if you get a final answer on each one, they'll perform exactly the same. But look at the difference in how we do this with a digital circuit, right? This is the sum of products. This is the product of sums. Okay, so the product of sums takes fewer gates. Okay. All right. Well, at least in this case it does. But in most cases, I mean, the sum of products, you just keep adding up all of those products together, and however many you have, if any one of those goes high, then the whole thing goes high. Okay. All right. Now let's start talking about the rules. And I always like to know what the rules are so I can meet the expectations, right? And so we have 10 rules that we're going to cover. And these essentially are, a lot of these, I would say 70 to 80% of these are common sense, but we're going to have a rule for it so that we describe what we're doing when we actually do the Boolean reductions, okay? So the first rule is anything ended with a 0 equals a 0. Yeah, right? Anything ended with a 0 is a 0. That's axiomatic. That's a rule. Rule 2, anything ANDed with a 1 equals itself, right? And here's a little truth table to prove that. So if one of them is always 1, then essentially it's going to pass through this other signal. That goes back to the description of the enable signal and the disable signal with the AND and the OR gate. So you might remember that from our discussions, okay? So essentially this is putting into a rule that phenomenon, right? Anything ANDed with a 1 equals itself. If you look at this as an algebra problem, anything multiplied by 1 is itself, if you want to think about it that way, right? Same thing here. Anything multiplied times a 0 is a 0. All right, rule number 3. Anything ORed with a 0 equals itself. Again, this goes back to in both of these cases here, we're talking about enable and disable signals. If you go back to the OR lecture, I think it was in the chapter 3 lecture. So anything ORed with a 0 equals itself, right? Because if this is a 1, well, then it's a 1. If it's a 0, then it's a 0, because this one is essentially taken out, because all you have to have is 1 high on any of the inputs, right? So anything ORed with a 0 is itself. Look at this in purely algebraic terms. 7 plus 0 equals 7. Same concept. Okay, so anything ORed with a 1 is equal to 1, and it doesn't matter what A is. All right, now this one you can't do a direct correlation because A would have to be 0 in regular algebra for this to be the case. Okay, so this is one of those ones that's not maybe as common sense. But when you think about the truth table in OR gate, it's still common sense, right? Since only one terminal needs to be high, A is kind of irrelevant here if this one is always high, right? So anything ORed with a 1 is equal to 1. Check comments here. Okay. Now let's talk about AND here. Anything ANDed with itself is equal to itself. This goes back to if instead of having 2 of them here, if I were to just have 1, if I were able to take these and connect it into 1A, it would accomplish the same thing, right? So they're either both 0 or they're either both 1. So anything ANDed with itself is equal to itself. So if we get some equation that's like BBAAA, x equals BB times AAA, then we could reduce the whole thing down to B times A, right? Because we don't need to AND it with itself over and over and over because it equals itself. Same thing with the OR. Anything ORed with itself is equal to itself, okay? They're either both 0 or they're both 1. Rule 7. Anything ANDed with its complement equals 0 because you only either have 0, 1 or 1, 0, right? That's just by definition of A being knotted, so to speak. That's obviously the definition. If you're going to AND those two together, then that's an easy thing to cancel out, okay? And this is another one of those where, I don't even know what A bar means in normal algebra, right? I know what prime means, but prime is different than the way that we use the apostrophe in digital, right? Prime means that you've taken a derivative, and that's got nothing to do with the bar. So this is A times its complement equals 0, Okay. Anything ORed with its complement is always 1 because, well, if this one is 1, then this has to be 0, right? And if that's 0, then that has to be 1. Okay. All right. Rule number 9. Anything double knotted or complemented twice will return to its original logic level. It's like using an inverter twice. So I like Kleitz's, I don't even need to write this one down. This is A getting connected to an inverter, comes out as A naught. You take that A naught through another inverter and you're back to where you started at A, right? Because we're in a binary mode here where you only have highs and lows. So this is also another thing I like to see. When I see the double bars, it's almost like if you ever played Tetris and you build up that one side to get the group of 4 to blast out a huge chunk. This is like when you see that skinny 1x4 column and you've got a place for it to land. That's the way I feel about this one. It just makes, oh, look at that. It just nicely cancels out. I can just get rid of it and not have to deal with it. So that's rule 9. Anything complemented twice returns to its original logic level. So if you had 5 of these, if it was A bar, 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 then it would go back to A naught, right? Because 1 bar would be A, and then if you switch back, if it's an odd number, then the bar stays. If it's an even number, then it goes back to whatever it was before. Okay. And finally, this one's got nothing to do with anything. This is a very specific rule. There's no mnemonic device for this. This one you just have to remember, and this is the very last rule, okay? This says that if you have a setup like this, where you have A or the complement ANDed with anything else, and this could be more than just B. This could be something else over here. Whatever the complement is ANDed with, it's like the complement just goes away, okay? Because then it's A or whatever this thing was ANDed with, okay? Same thing goes if you find the opposite true. If you have A naught plus AB, well, you just get rid of the A, and now it's A naught plus B. So if you're trying to figure out how, you get to a certain point and you come up with this and you're like, I can't factor out an A, I can't factor out a B, I'm done, right? Well, no, you're not done, because if you use Rule 10, you can further reduce this down to just a single gate of A plus B, okay? So, and this, this is using truth tables to prove it, but I just want you to remember this. All right, now I'm going to flip over to the next slide, and this is table 5.2 out of your book. And if we were meeting in class, this is something I would say this needs to be on your crib sheet for the exam. All right, it's good to have it written down. You don't have to memorize what each rule is. I still don't have them all memorized. All right, and I've even gotten more lazy about it in class because I make you tell me what rule it is, right? The only one I remember is the 10th one because it doesn't have anything to do with anything else. It's just kind of like a special rule there. So anyway, this is essentially everything that we just did without any words. It's just showing you the different types of equations, right? Anything ORed with itself is itself. Anything ANDed with itself is itself. That kind of thing. Okay, any questions so far? I think we're moving right along here. All right, what do we got here? Okay, so it says, which Boolean laws are illustrated below? Okay, well, in this case, I have B or D or E. And what I'm saying here is that this, if I do D or E first, and then I OR that with B, that should give me the same result as if I did B or D first and then took that result and ORed it with E. Okay, it should be exactly the same. So which one of these laws accomplishes that? So which law for the first? Which law for the second? Which law for the third? How many of them are there? I have to switch back over here. Come back down here. Okay, so there's 4 of them. Okay, so could you tell me what all 4 of those are? For the fourth. Okay. So if I go back to my laws, the first one says that the order doesn't matter. The second one says that for addition and multiplication, I can do individual pairs before I do the entire thing, right? Something to that effect. And what did we call Rule 2 or Law 2? Right? Is it the associative? The commutative implies that things are moving around, right? And the associative means that I'm going to put the parentheses around these 2 variables first and then go. All right, what about the next one? The next one is AB or BA. That is commutative. That is law number 1, commutative, because the order does not matter. The next one, A plus B plus C, is the same thing as B plus C plus A. I think that's, again, the commutative, the very first one. And then finally, we have what I would call the distributive law. Okay? Now, it says, what are some strategies for remembering the 10 Boolean rules? I don't have a good mnemonic device for this, and so my strategy is just write it over and over, or start teaching college one day and then let your students do the work for you. That's my strategy right now. It's not a very good one, but I know where to look if I need it. I just know what they are. I just don't remember which number they are because I'm just so used to doing this breaks it all the way back down to the foundation for me. I just have assumed those rules for so long that I still don't know the order. So, I'm not going to make you remember the order. I just want you to be able to use them, okay? All right. Well, let's keep on going. So what's the whole point of all of this? Yeah, that's great. We see some laws. They sometimes resemble the algebra laws. And so this says that equivalent circuits can be formed with fewer gates, right? Cost is reduced, reliability is improved, and the way we do this is we use the rules and laws of Boolean algebra. We can also use DeMorgan's, which is going to be coming after this, okay? My camera just flipped off. It's got some kind of an auto off on it still. So let me restart that real quick. There it is. Okay. All right, so that's the whole point of this, is we want to get down to using the fewest gates possible. All right, so here we go. So it's to simplify the logic circuit shown by using the appropriate laws and rules. Okay, well, we see here that we have A plus B out of this gate. We see that we have B and C out of this gate. Those 2 quantities are ANDed together here. And then this quantity is then ORed with A. Okay, so I'm going to write that equation on the board here. And so we had x equals A or, what was the rest of it? A or the quantity A plus B, in parentheses, that quantity times BC. All right. So let me switch over to the board now. So there I've got x equals A. That's not showing up very bright. X equals A plus the quantity A plus B, that thing times B times C. All right, so what I'm going to do is I'm going to go ahead and FOIL this out. So I've got A. So I'm using law 3 to do that. Okay. So I'm using the distributive law, and I get A, B, C plus B, C, B. Okay. All right. So I notice here, I notice a couple of things. I noticed that these two things have B's and C's in common. But if I factor out a BC from that, I'm left with B plus A. That doesn't really get me, well, yeah, that doesn't really get me anything yet, okay? I do see that if I pull an A out of this one, you know, if I were to pull an A out here, I'd be left with 1 plus BC plus BCB. What rule is that where I can factor out? I think, again, that is law 3, right? The distributive law allows me to pull a term out if they both have it, and it also allows me to distribute the term to everything inside the parentheses. So that's legal to do. I used law 3 to pull this out. I rewrite the rest of the equation as it's supposed to be. I'm now up against the rule, aren't I? Anything ORed with a 1 is a 1. Okay, I'm actually going to go over here and find, because I don't know it off the top of my head, I'm going to go over here and find what that rule is. So anything ORed with a 1 is a 1. That is rule 4. Okay? Rule 4. That means I now have A times 1 plus BCB. Okay, and I am going painstakingly so. You may already see what the answer is, right? Here I've got A times 1. Okay, now, what law do I have, or I'm sorry, what rule do I have that lets me reduce that down to A? Okay, so anything ANDed with a 1 is itself. That is rule 2. So we used rule 2 here, and that gives us A plus B, C, B. Okay? So now I've got anything ANDed with itself is itself. Let me switch back over and find which rule that is. Anything ANDed with itself is itself. That is rule 5. So rule 5. I don't think we go anywhere farther than that, but there we go. So here's my original circuit, and in that one, how many gates did we use? Well, we used 1, 2, 3, 4, right? We used 4 gates. Now we're down to 2. We can say BC, whoops. Take that, OR it with A, and there we go. So we went from 4 gates all the way down to 2 gates. That makes your boss happy when you do something like that. All right, let's go ahead and keep going here. And switch back over. So it says simplify the logic circuit shown below. Logic shown by using the appropriate laws and rules. Okay. All right. Well, I can do that. Let me go back over to the board and erase what I've got, and then I will put this one up. So I'm going to do it from the gates here. I've got A, B, and C there, right? So A, B, C. And we've got an OR and AND. So let's follow this at each point here. All right, the output of this gate is A plus B. The output of this gate is B times C. the output of this gate, A plus B times BC. Okay, now, that's a little bit different than what we just had, right? So, let me go ahead and what I like to do is I like to start here and then work it like a math problem. So the first thing I'm going to do is law 3. I'm going to distribute this out. So now I've got ABC plus BCB. Okay. I am going to go ahead and do this one right here. Anything ANDed with itself is itself. I believe that's rule 2. Okay, so now I've got ABC plus BC. I notice that I have both a BC term in both of these, and so I'm going to pull it out. So I'm just doing, you know, a lot of this stuff, it's similar to how we do algebra, okay? Regular algebra. I see a BC term in each one, so I'm going to pull it out. That's law 3 that lets me do that. So BC times A plus what's left over here, 1, right? Because BC times, if I distribute this out, that's ABC plus BC times 1, okay? So for that one, now I have something, anything ORed with a 1 is a 1. See, I've already forgotten what it is. I don't try to commit these to memory. Anything ORed with a 1 is a 1, rule 4, and I just used it too. All right, rule 4. So that's going to become a 1. And now I'm back to anything ORed with a 1 is itself. Anything ORed with a 1 is itself. That is rule 2. Because I just had it up here. I'm sorry, anything ORed with a 1, not itself. Anything ORed, ANDed with a 1. Jiminy. That one's ANDed with itself. That one should be rule 5. Sorry about that. This should be rule 5. Okay, because that's anything ANDed with itself. Rule 5. Rule 2 is anything ANDed with a 1 is itself. There we go. So what did we determine about this? Well, A has nothing to do with it. It doesn't matter at all. We were able to completely eliminate that variable. Okay, so that also would make your boss happy because now you just went from 3 gates down to 2. Or I'm sorry, 1. 3 gates down to 1. All right. Any other questions? Okay. Let's keep on trucking here. And we'll get down to... So as I said before, it says Quartus 2 software determines the simplest form of an equation during compiling. It eliminates unnecessary gates and minimizes the number of gates in the FPGA. So if you do a really poor job and you have a bunch of extra gates that are not necessary, Quartus isn't going to tell you that. They're just going to do it so that when it makes the connections internal inside the chip, it only uses the resources it needs. And so it actually does a reduction for you. All right. So the next portion of this, so you can see how, you know, we could do those all day. If we're just going to use AND gates and OR gates, then we can do this combinational logic all day long, right? Sum of products, product of sums. Once you start adding complements, okay, now we have to use something called DeMorgan's theorem. Okay, and I think, oh my goodness, I think I called this... I called it DeMorgan's law. I mean, I don't think it's a law. I think it's just a theorem. So it's DeMorgan's theorem. So used to simplify gates containing NAND and or NOR gates, right? So when you just look at the totality of it, which this describes everything that happens, if you have a quantity under a, and I've gone over this before, if you have a quantity where the output is inverted, okay, you can break that down and switch it to, if you break the bar and distribute it to each input and then change the sign between them. So this was an AND, that now becomes an OR. And this is A and B, the whole thing knotted, is how I would say that. And so that breaks down to A naught or B naught individually. Okay? Same thing if you have a NOR situation. All right? So we've got A plus B, the whole thing knotted, equals the individual inversion of A and the individual inversion of B. So A naught and B naught. Okay? Now, you can also go backwards from this. So if you have this, you could go the other way. Okay? If you have this, if you have this right here, then you can go backwards into this. So this starts to explain the universality of NAND and NOR gates, right? Because you can use them to perform, we know that if you put one signal into a NOR gate, or if you put only one signal into a NAND gate, it becomes an inverter. So literally, you can program your entire circuit with just NAND and NOR gates if you wanted to, okay? And you can see here, we can accomplish any of that if we used enough gates. It wouldn't be the most cost-efficient way. We're trying to accomplish the most cost-efficient way right now, okay? So here's another way to say it. Break the bar over the variables, change the sign between them. Okay? It says inversion bubbles used instead of inverters to show inversion. I use the bar if we're talking about so what it's saying by inversion bubbles is you don't have to put an entire NOT gate there. Just put the little bubble, even if it's on the input. And I'm gonna switch back to the camera and show you what I mean. And it says use parentheses to maintain proper groupings and results in a sum of products form. So we are going to get down to this, but you'll see that we're going to be perfectly okay getting down to this point right here because of where we start. Okay, now this is all a result of what's called bubble pushing. Right? In other words, you take any gate, any configuration, and if you note that things are bar or just right, so this would be A naught or B, right? For bubble pushing, what you do is, and it's essentially DeMorgan's, right? You invert all of the inputs and outputs, and then you change this sign. So see what happens here. Just a regular AND gate. I'm going to invert every single input and output, and then I'm going to change the sign between them, right? So there's the drastic case. Right? If I come down here and I have both of these inputs, so this one would be C naught and D naught. Okay? If I bubble push and invert all of them, right, that'll double invert to a regular, that'll double invert to a regular, and this will stay inverted. So you see that the output's the only thing inverted here, and then I change from an AND to an OR. Okay? If you notice in the equations here, that's all we're doing, right? This one is not. You can see here that the A is not inverted, the B is not inverted, but the output is. Now you can see over here that A is, B is, and the output is not. Otherwise, there would be a bar across the top, and then we change the sign. This is all we're doing, right? This is the algebraic description of what's happening here to get the other gates. Okay, we're just bubble pushing. Okay, and let's look at this one down here. So this one is E naught or F, the whole thing knotted, right? Because that's a NOR gate. And so if I bubble push that and I invert everything, I'll be left with an F inversion and change the OR to an AND. Okay? So like I said, pretty straightforward there. And again, this goes into a little bit more detail. Like I said, add bubbles to the inputs and outputs where there were none and remove the original bubbles. Okay? Just go, if you have to, just replay what I just said until it makes sense. Okay, because that's all we're doing here. It's like playing a little game. Invert all the inputs and outputs, change the sign between them. That's it. And here we go. So the NAND as an inverter, all right? And essentially, we're using this right here. Underneath the top, we have A and A, the whole thing knotted. Well, A and A is A, and A knotted is A naught. Right? And so you either have 0, 0 or 1, 1, and it's going to change. It's going to invert it on the output. So this functions as an inverter. Okay? Same thing for a NOR gate. Okay? You're either going to have 0, 0 or 1, 1 on a NOR gate, And it functions exactly the same way, because anything ORed with itself is itself, and then if you invert the output, it's gonna turn into an inverter. Okay? Now, if you want to have an AND gate, right, and all you have available are NANDs, well, when you have this configuration here, if you say A and B, the whole thing knotted, right, that's A and B NANDed, if you take that result and then put it through an inverter, this inverter cancels this bubble right here, and so you're back to an original AND. The way that we would do that with DeMorgan's is X equals A and B, the whole thing knotted. This will invert the entire thing. So again, A and B have already made their way through the output here. And so it's the output that gets inverted out here, right? The output gets inverted, and then the output gets inverted again. That's why you have the double bar over the top. And we know with our rules that anytime you double invert something, it's like that 1x4 column in Tetris, right? You get to clear the whole thing out, and then you're just left with the AND. Okay? Same thing if you wanted to do an OR, right? If you wanted to create an OR with NORs, you would take A and B NORed together and then send that signal through a NOR, right? Just a single. So it would invert twice, and you'd be back to the original A or B. So that's what we're talking about when we say the universal capability of NAND and NOR gates, that we can create any gate that you want. You can create AND gates, you can create gates where, you could create A, NOT, or B, right? So, you can use as an inverter before it gets to the OR gate with A. So here's another one. This is what I'm talking about. So we've got, this is forming an OR. So here's the OR right here. All right. If we invert everything, so we invert A and B and the output, which is what's up here, and then we change the sign between it, now we have A naught and B naught, the whole thing knotted, right? We have A naught and B naught being sent through a NAND gate, and that equates to an OR. All right, so that's what we're saying here is that, I don't have an OR gate, but I have a bunch of NANDs. Well, I'll just make one out of that, okay? And here's a NOR with 4 NANDs. You can see that this right here, this one is replacing this, right? And so we have that original one, and the whole thing works out to a NOR here because we have to invert it twice. So this was an OR. To make it a NOR, we just invert the output, right? That's all we did from that slide to that slide, is we just took the output here and then inverted it. Okay. And I think that's where we go as far as we go today, because now we're going to talk about K-maps, and that is a discussion for next time. Okay, I don't believe we get into K-maps today. Let me consult the syllabus. I believe it is next time. Yes, it is. Okay, so I actually just did a little bit of the next time anyway with the NAND and NOR gates. I shouldn't have gone that far. That's okay. All right, so here's what I'm going to do now, is I'm going to switch back over. I'm actually going to go into Firefox here, and I'm going to go back to here. And if you want to follow along, this is where I'm going, and this is why I don't have it already pulled up, because I wanted you to see me do it. So I'm going to go to Modules, and I'm going to scroll all the way down to today's class, where you see Lab 6 and 7, Boolean Algebra, DeMorgan's. Click on that. It's in Session 7. And I'm just going to open up the first one for now. So this is Boolean Algebra and NANDs. Okay, and I'm going to go ahead and start working through this. So again, if you're participating right now, you're getting credit for this lab. Okay, let me go ahead and switch back over now to my desktop. Okay, so here we go. So this is the Boolean reduction, And again, we're not doing anything special because this is virtual. This is what I've started to do the last couple of semesters, over the last couple of years here actually, just because there's so much to this and I want to make sure we get it all right. Okay, so all this first stuff here is just an introduction. You know, this one is explained here. Okay, so we want to get all the way down to this part. Right? Now, as I'm looking at that, I believe that's the one from the PowerPoint. I don't want to do that one again if we already did it earlier. Is it the same one? No, it is not the same one. Okay, very good. Solves that. All right, so let me go ahead and write this on the board, and if you want to write this down too and follow along, give you a chance to do that because I'm going to write it up here. Normally I would project this onto the screen in class and I would just do it from there, but okay. So we got an or, and. And so that one's an A. That one is B. And if we did this one already, no big deal. I'm going to do it again. And then that one is C. And then those go into the AND gate. And this comes back up here. And then we have our final X. Okay. Okay, let me have the YouTube pulled up in my background here so I can see you all. Okay, so here we go. I'm going to go at each point here. Wonder if this one is still good or not. Okay, it is. All right, so the output of this gate is A or B. The output of this gate is BC. That output then is the quantity A plus B times BC. And this is looking like the other one. And then so finally we have X equals A or A plus B BC. Okay? All right, well, I'm going to go ahead and use Law 3 and distribute that out. A plus ABC plus BCB. And let's see here. This is the one from earlier. Oh, well, we'll do it again, okay? So let's do it the other way this time. Let's go ahead and start here. All right, so I noticed that I see B times B, and if I have that pulled up here, this will make this a little easier for this part. Scroll back up to the rules, and the rules say that anything ANDed with itself as itself, that's Rule 5. Okay, so anything ANDed with itself is Rule 5. So now I've got A plus ABC plus BC. Okay? So I'm doing a completely different approach this time, and I should come up with the same answer. It doesn't matter how you do this. This time I'm going to notice that there's a BC in these two terms. Okay? And I'm going to go ahead and pull that out. So now I've got A plus BC times A plus 1. Okay? And I did that distributive law, so that's Law 3. Now this one, I know that, if I switch back over here, anything ORed with a 1 is a 1. That is Rule 4. So now I'm left with A plus BC times 1. Anything ANDed with a 1 is itself, and that's rule 2. So this time I get same thing as last time. A plus BC. Okay? So again, you may look at that and try to do 2 or 3 of them in one line. And as long as you get the right answer, I don't really care if you do that, okay? Just got to be careful because you don't want to miss something. I'm being very explicit and taking this a little over the top so that you can see every little step of the way how we get to the end answer. Okay. Get this down and get this back up. So there we go. That's what we just did. All right, now let's look at the next one. Now, let's see. It says repeat the procedure in steps 1 through 4 for the circuit in figure 6.3. That's here. Complete the truth table. Okay, so what we're going to do is we're going to come up with an equivalent circuit given our rules. Okay, so I'm going to go ahead and now write this one on the board. And again, I've got to erase what I've got. You can go ahead and start writing this one down for reference. So what do we have here? We've got or, and. Or, and. That's A. B goes to here, but then it goes through that inverter there. And C goes here. Okay. All right. So the output of this gate right here is B naught. The output of this gate is A or B naught. Output of this gate is B or C. There goes my camera. Can't just do what it's supposed to do. All right. And the output of this AND gate, now we've got A plus B naught times B plus C. And then in the final one here, we've got X equals B times that whole quantity up there. Okay? Now, I'm going to let you have a head start on this, and I want you to try to see if you can reduce this down, and then I will lag behind you and see what I come up with. So go ahead and try this on your own right now. All right, that should give you a good head start. If you're still working on it, no big deal. Okay. Well, first thing I'm going to do is I'm going to distribute this out. So I guess I'm using law 3. And so I've got AB. Well, how about this? I'm just going to do the FOIL on the parentheses first, and then I'm going to leave this B outside for now. Okay, so this is going to be AB plus AC plus B naught B plus B naught C. Okay, now I could go ahead and reduce some of this stuff down now, or I can just distribute it all out and just have a great big sum of products form. So that's what I'm going to do. So law 3, so now I've got ABB plus ABC plus B naught BB plus B naught CB. 1, 2, yeah. Okay. So in multiple places here, we've got the rule that says that anything ANDed with itself is itself. Okay, and I think I've got that memorized for today. That's rule 5. So I'm going to take care of both of those at once. So now I'm left with AB plus ABC plus B naught B, because remember all I did was this rule 5 with these two, plus B naught C B. Now I see two cases where I have something ANDed with its complement, which I know is a 0, right? Because you either have 0, 1 or 1, 0. So I'm going to say with the rule, the complement rule is rule 7. Okay? Those, and so now I'm left with AB plus this converts to 0, right? So because B naught and B are never going to be 1, and this same thing here. So those all equate to 0. So if I wanted to, I could say, plus 0, and then say anything ORed with a 0 is itself. Okay, I'm not going to go that far because I'm running out of room here. So I'm just going to deal with what you see here. Okay, I see AB plus ABC. I see that there's an AB in each term. Use law 3 to factor out. 1 plus C. Now I'm going to use the rule that says that anything ORed with a 1 is a 1, and that's rule 4. And so finally I'm left with AB. So C has nothing to do with this circuit. It does not, what I should say is it does not affect the output of the circuit. Okay? So X is only equal to AB. So there are 1, 2, 3, 4, 5 of these that reduce down to a single gate. Okay, let's see how everybody did here. Anybody? I just blew through that. I could have made a mistake that's glaringly obvious. I don't know. Anybody get something different? Okay. If I'm just looking over the work again, that's AB plus AC plus B naught B plus B naught C. I think that's okay. And then we multiply the B through there. And Steve says I wrote the schematic wrong. Well, that'll do it. That will do it. Yeah, those are ors and then 2 ands, and I've got ors and then 2 ands. Yep. All right. Any questions on that? It says attached to C output gate instead of B. Ah. Yeah, that'll give you a different answer for sure. So you can see there, I could have expanded this out to give us a couple more steps, but, kind of running out of room. No big deal. let's keep going and see what we have next here. And here we go. Here's some, the bubble pushing and how to come up with inverters and all that good stuff. Okay. And here we go. This is what I was looking for. Okay, so we want to reduce the, let's see. I think this is the last one on this lab. So let's answer these questions real quick. What's a major advantage of gate substitutions? Well, money, 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 right? If you're going to make something and you're going to make a bunch of them and you're going to, try to make money off of it, you want to try to make it as cheaply as possible. So why would you include extra IC chips if it's not going to give you a return on your investment? Plus, it takes up space on the PCB board, and that means you have to make a bigger PCB board. And so, then that also means that you have to use a bigger case if that's what you're doing. So, it compounds because you have to take up more real estate on that PCB board, the printed circuit board. Why are AND OR gates called non-inverting? I think that's pretty self-explanatory. They just perform a logic function. They're kind of in their own little world. Once you start adding knots, that's when you start getting some other equations. But AND and OR are just providing logical functions. And we talked about that with the cars, right? Where the dome light is an OR situation where any combination of your driver's side door, your passenger door, your manual light, it can come on with a manual switch at the top of your vehicle, right? And if you wanted to start your vehicle, like my one student, where you have to have all of the things happening at once, right? The AND situation. You got to be sitting in the car. You got to have your foot on the brake. Got to have your key fob within the perimeter of the vehicle, and you have to push the push button to start it. All of those things have to happen, or the output won't go high. So those are logical functions, AND and OR. Those are non-inverting. Once we start inverting, we start getting NAND gates and NOT gates and NOR gates and things like that. All right, so this says reduce this expression to its simplest form, but let's go ahead and answer this real quick just to reiterate. Why are NAND and NOR gates called universal gates? Because you can make any other logic gate that you want using only NAND and NOR because of their inverting properties. So you can tie the input of each gate together to have one single input, and so you either have 0, 0 or 1, 1 on the input, and that makes each gate an inverter. And so that can be exploited to make other gates, okay? This is not the most efficient or the most cost-effective. It's just saying that you can do it if you want to. All right, so here we go. Here's the expression. All right, so you can go ahead and write that down. I'm going to write it up on the board. Now this one, we're just forgoing the gates altogether, and we're just going to do a strictly Boolean algebra reduction. I'm going to assume, Steve, you were with me yesterday. Is the audio okay? Can you leave me a comment, please? Have I cut out today at all? Does it matter if I'm turned this way or if I'm turned this way? I think the problem is coming in maybe at this connection or this connection, and so I'm trying to keep them from being strained when I turn. Okay, so x equals, and now we've got that at the end, but that's okay. So we've got a naught plus b, and then b plus c. A naught plus b, b plus c. And we multiply the whole thing times b. Okay? All right, now let me go ahead and switch over here. Oh, great. He says audio's been great so far. Outstanding. I was up late last night worrying about that, and this is the only thing I can come up with. So it's kind of a pain in the butt until I get a new one, but I'm glad that it's working. Okay. So let me switch back over to the board here. There we go. All right. Let's reduce. Okay, so I'm going to go ahead and use rule 3. I'm sorry, law 3. I keep wanting to call it rule 3, but law 3, where I distribute this out. And I'm going to do it all at once, too. Okay, so I've got B, B, A naught, because I've got A naught times B, and that I have to distribute that to that term. So that's B, B, A, plus, now I'm going to do the outer, A naught C times B, so A naught B, C. The inner, B, B times B, so Better Business Bureau, plus B times C times B. Okay, so I just did a full FOIL in just one step. Now, you could have just done the inside and FOILed these two things together and then distributed the B throughout, okay? So I notice in a few places here, wow, this one, and this one, that's rule 5. Look at that. I got rule 5 down today, that's it. I'm still getting 2 and 4 confused. So I'm going to go ahead and take care of this one. So now I've got A naught B, I'm sorry, plus A naught BC, plus that whole thing reduces down to a single B. Ooh, I can see it already ahead of me here. So now this reduces down to BC. Okay? I'm going to let you go from here. I should have let you go from the top one, but I wasn't thinking. So go ahead and get started. You know, we used rule 3. Essentially, all I've done is, law 3. I distributed everything out, and now I've done one single reduction where I've said that anything ANDed with itself is itself, rule 5. All right, so go ahead and keep going here. Okay, Steve has it. But go ahead and try this on paper. Let's see, as I'm looking at it here, 1, 2. You can do this in 2 steps after this. You could also do it in like 5 or 6 steps. Anybody else get any answers? Okay. Okay. So even if you're not done, I'll just point something out here, okay? But then I'm going to go do it the long way. Every one of these terms has what? They all have a B. If I pull that B out, and I'm going to erase this in a second, but I'm going to pull that B out, I'm left with A naught plus A naught C plus 1 plus C. That whole thing, because of that 1 right there, reduces down to a 1. B is your answer. Okay? I'm going to do this the hard way. Let's say I didn't notice that that was the case. All right? Let's just start with these 2 terms. I see that there's an A naught B in both of these. Okay? So I'm going to factor out with law 3 and say A naught B times 1 plus C plus. I'm going to do the same thing over here. I'm going to pull the B out of these 2 terms because I'll be left with a C plus 1 there. So B and then 1 plus C. And so that's what law 3 got me down to here. And now I'm going to use anything ordered with a 1 is a 1. which is anything ORed with a 1. Ah, it's rule 4. So now I'm going to use rule 4. And those convert down to a 1, so now I'm left with A naught B times 1 plus B times 1. Anything ANDed with a 1 is itself. That is rule 2. Rule 2. So now that leaves me with A naught B plus B. Okay? And I think you can see from here that if we go ahead and use law 3 again, pull a B out, we're left with A naught plus 1. And again, we're in this situation here, so if we use rule 4, we're ending up with B times 1. Now we have this situation, we use rule 2. So it's just B. A and C have no impact on the output of this digital circuit at all. So Steve, you were correct. You get a gold star. Kofi got it. David got it. All right, very good. Very, very good. That takes us through lab 6. Okay? So, we got one more to do here. I'm going to go ahead and close out of that. I'm going to come back to our modules, and then I'm going to open up this DeMorgan's, lab 7. Okay, so this one says construct the circuit well, let's go ahead and what we're going to do is we're going to take this right here. I'm going to write this on the board, and then I'm going to write out the full equation, and then we're going to use DeMorgan's to reduce it down. Okay, so let's go ahead and do that. I'm going to leave this right here. Oops, you can't see what I'm doing there. Here it is. I'm sorry, I thought I was over. Okay, so what I was doing was I came back over to lab 6 and 7, and I opened up DeMorgan's, and that's this, and I've scrolled all the way down to the procedure, which I guess is page 3. And so I'm going to write this on the board, and then we're going to go ahead and solve it using both DeMorgan's and Boolean. You have to use DeMorgan's first so that you can eventually use all the Boolean rules to reduce down. But you got to get rid of the DeMorgan stuff typically first. Sometimes you do it, DeMorgan's and then some Boolean and then some DeMorgan's, but in general, you want to get rid of all those bars so that you can start using the rules. So let me go ahead and copy this down. So that is a NAND up there. So now we are introducing, the reason why this is different is because I know that we had a NOT gate before, but you see that the way that the circuit was constructed, that was easily taken out, okay? So now we're starting to use inversion on the outputs. So we've got a NAND gate, we've got a NOR gate. Okay, and those have inputs of A, B, and C. Okay, and then out of those we take it into an AND gate. Lots of fun. I think this is fun. This is like digital Sudoku. Okay, let me switch back over to the board. Whoa, about lost it. Okay, so what is the output of this gate? A and B, the whole thing knotted. That's a NAND gate. This one is a NOR. We have B or C, the whole thing knotted, because we're inverting the output. We're not inverting the input in either case. In the last example, that's what we did. We inverted the input, right? Okay, so now I'm going to take that quantity and AND them together. So I come up with an equation that looks like this. The whole thing knotted times B plus C, the whole thing knotted. All right. All right. I'm going to go ahead and let you try to get started on this and see if your approach is the approach that I would take. Now, you have two different ways that you can approach this. You could deal with the AB term first, or you can deal with the B plus C. It doesn't matter which one you start with, at least not to me. Okay. Let's see what I would do. Well, I don't really have a preference one way or the other, and so I'm just going to work this side first, okay? So I'm going to use DeMorgan's, and I'm going to go ahead and, remember, I'm going to just break the bar, distribute it, change the sign. So A naught plus B naught, okay? I'm going to rewrite this term. I'm going to use DeMorgan's again to get rid of that bar now. So I've got A naught plus B naught times, break the bar, distribute it, change the sign, B naught and C naught. Now I'm going to use Law 3, goodness, and distribute that out. So now I've got A naught, B naught, C naught, plus B naught, C naught, B naught. Okay? I'm finally down to the place where I can now start to use Boolean algebra. All right, well, doesn't do me any good to pull out the BC's because I'm left with A naught plus B naught. That doesn't do me any good. But I can get rid of this duplication here, and so that's Rule 5. Anything ended with itself is itself. So now I'm left with A naught, B naught, C naught, or B naught, C naught. I see that there's a B naught, C naught now in each one of those terms, and so I'm going to use Law 3, and I'm going to come back up here to the top and say, I want to say x equals A naught. No, I don't. I want to pull the BC out, the B naught, C naught out. So B naught, C naught. And I'm left with A naught plus 1. Okay? Anything ORed with a 1 is a 1. Is that Rule 4? Rule 4, anything ORed with a 1 is a 1. Look at that. So that's rule 4. So now I'm left with B naught, C naught times 1. Anything ANDed with a 1 is itself. That's rule 2. I'm left with B naught and C naught. Is that what everybody else got? Did I go too fast? So, anybody get anything else? How do we write knots in chat? Okay, so the way that I would write that is probably like this, something ridiculous like this. What was it, B and C? Yeah. B naught times C naught. Like that. Yeah, the way you have it is fine also. Yep. Either way. All right, very, very good.